Every few years, a new technological shadow appears on the horizon, and with it comes a familiar question, spoken half in curiosity and half in fear. This time, the question sounds like this: will quantum computers destroy Bitcoin? At first glance, it feels like a modern myth in the making. Bitcoin, the digital asset built on cryptography and mathematical certainty, standing defenseless before a machine that bends the rules of reality itself. Headlines exaggerate. Social media panics. Words like unstoppable, inevitable, and endgame are thrown around carelessly. And once again, humanity finds itself staring at a creation of its own intellect, unsure whether to celebrate or to run. To understand why the fear feels so intense, we have to remember what Bitcoin truly represents. Bitcoin is not just code. It is not just money. It is an agreement written in mathematics, a system that replaced trust in institutions with trust in logic. No armies defend it. No governments guarantee it. Its security rests on one fragile assumption, that the mathematics behind it remains unbreakable within any realistic time frame. For more than a decade, that assumption has held. Bitcoin has survived crashes, bans, internal wars, forks, and endless criticism. But quantum computing feels different. It doesn't attack Bitcoin politically or economically. It threatens it intellectually. It questions the very foundation on which Bitcoin stands. Quantum computers are often described as magical machines, capable of solving problems no classical computer ever could. They don't calculate faster in the way people imagine. They calculate differently. Instead of living in a world of ones and zeros, they exist in a probabilistic realm where outcomes overlap, interfere, and collapse only when observed. To the human mind, trained in linear logic, this feels unsettling, almost alien. And when people hear that such machines could, in theory, crack cryptographic systems, fear fills the gaps left by understanding. The narrative becomes simple and dramatic. Bitcoin uses cryptography. Quantum computers break cryptography. Therefore, Bitcoin dies. But fear thrives in simplification. This fear is not new. Humanity has felt it before. When electricity was first introduced, people believed it would kill cities. When early trains reached high speeds, doctors warned the human body could not survive such velocity. When the internet emerged, it was accused of destroying attention, morality, and society itself. Each time, the fear was real, but incomplete. What makes the quantum fear particularly powerful is that it attacks something abstract. We cannot see cryptography. We cannot intuitively feel computational hardness. We simply accept that certain problems are too hard for computers. Quantum computing dares to challenge that belief, and in doing so, it shakes our sense of certainty. Bitcoin, in this context, becomes a symbol larger than itself. It represents a world where rules are fixed, supply is finite, and mathematics does not negotiate. The idea that a future machine could undermine this feels like betrayal by progress itself. But here is the uncomfortable truth we rarely confront. Bitcoin was never meant to be protected by stagnation. It was born from adaptation. It emerged as a response to financial systems that failed to evolve responsibly. Its creator understood that systems survive not because they are perfect, but because they are honest about their limitations. Quantum computing does not represent chaos. It represents intelligence exploring a deeper layer of reality. The fear arises not because quantum computers exist, but because they remind us that no system is immune to progress, not even one built on mathematics. And yet, fear often confuses possibility with inevitability. The mere existence of a theoretical attack does not mean collapse is near. It simply means the conversation must mature. Bitcoin does not exist in a vacuum. It exists in a world where every bank, military network, satellite system, and secure communication protocol relies on cryptography as well. If quantum computers truly reached a point where they could effortlessly break Bitcoin, they would have already dismantled the foundations of the modern world. That perspective is often missing from the panic. Bitcoin is not the weakest target. If anything, it is one of the most transparent. Its rules are public. Its assumptions are known. Its vulnerabilities, real or imagined, are debated openly. Traditional systems, by contrast, hide behind obscurity and centralized control. The fear of quantum computers is, at its core, a fear of losing certainty. Bitcoin gave people a sense of solid ground in a financial world built on promises and debt. Quantum mechanics tells us that reality itself is probabilistic, uncertain, and strange. When those two ideas collide, discomfort is inevitable. But discomfort is not destruction. This first encounter between Bitcoin and quantum computing is not a death sentence. It is a mirror. It reflects our tendency to mythologize technology we do not yet understand and to underestimate the resilience of systems designed to evolve. Before asking whether quantum computers will destroy Bitcoin, a better question emerges. Quieter, but far more important. Are we willing to let our systems grow alongside our intelligence? Or do we expect progress to stop the moment it challenges our comfort? The answer to that question will shape not only Bitcoin's future, but our own. Once fear has taken hold, clarity becomes difficult. Quantum computers suffer from this more than most technologies. They are often spoken of in absolute terms, either as world-ending machines or as distant science fiction toys with no real impact. The truth, as usual, lives somewhere in between. To understand what quantum computers mean for Bitcoin, we first have to dismantle the mythology surrounding them. A classical computer, the kind that runs your phone, your laptop, and the global financial system, works with bits. Each bit is either a 0 or a 1. Everything you see on a screen, every transaction ever made, is ultimately reduced to long sequences of these two states. Speed comes from doing this very fast, billions of times per second. But the logic itself never changes. Quantum computers operate on something fundamentally different. Their basic unit, the qubit, does not obey the same rules. A qubit can exist in a combination of 0 and 1 at the same time, a property known as superposition. When multiple qubits interact, they can become entangled, meaning the state of one instantly influences the state of another, regardless of distance. This is not a metaphor. It is how nature behaves at its most fundamental level. Because of this, quantum computers are not faster versions of classical machines. They are specialists. They explore many possible solutions at once, then use interference to amplify the correct answers and cancel out the wrong ones. For certain mathematical problems, this approach is extraordinarily powerful. For most everyday computing tasks, it offers no advantage at all. This distinction matters. A quantum computer will not suddenly make video games run better, websites load faster, or spreadsheets calculate quicker. Its power is narrow, focused, and fragile. And fragility is a word rarely associated with the way quantum computing is discussed in public. Quantum systems are notoriously difficult to control. Qubits are extremely sensitive to noise, temperature, vibration, and electromagnetic interference. Maintaining a stable quantum state requires near absolute isolation, temperatures colder than outer space, and complex error correction schemes that themselves consume vast computational resources. What looks omnipotent on paper becomes delicate in reality. This is where the conversation about Bitcoin often loses balance. The cryptographic threat usually centers around one algorithm in particular, Shor's algorithm. In theory, a sufficiently powerful quantum computer running this algorithm could break widely used public key cryptography, including the elliptic curve signatures Bitcoin relies on. The keyword here is sufficiently. The gap between theoretical possibility and practical execution is enormous. Running Shor's algorithm at a scale that could meaningfully threaten Bitcoin would require millions of stable, error-corrected qubits operating coherently for extended periods of time. Today's quantum computers operate with dozens, or in experimental cases, a few hundred noisy qubits. The difference between these two realities is not incremental, it is exponential. This is not a matter of waiting a few product cycles or a clever engineering shortcut. It is a frontier problem in physics, material science, and information theory all at once. Even the most optimistic researchers acknowledge that large-scale, fault-tolerant quantum computers remain a long-term goal, not an imminent breakthrough. Yet fear compresses timelines. A discovery in a lab becomes a headline about collapse. A theoretical paper becomes a countdown clock. Bitcoin, being both misunderstood and emotionally charged, becomes an easy target for these narratives. Another common misunderstanding is the idea that quantum computers break all cryptography equally. They do not. Some cryptographic schemes are vulnerable to quantum attacks. Others are not. Hash functions, which play a central role in Bitcoin mining and block security, are far more resistant to quantum advantage. Even in a quantum world, brute force remains brute force, only modestly accelerated. This nuance is rarely discussed because nuance does not spread well. Panic does. What is often overlooked is that cryptography itself is not static. The same scientific community exploring quantum computing is also developing quantum-resistant cryptographic algorithms. Governments, corporations, and standards bodies are already preparing for a post-quantum world, not because collapse is imminent, but because preparation is rational. Bitcoin exists within this same technological ecosystem. It is not isolated. It does not rely on secret algorithms frozen in time. Its security assumptions are public, debated, and continuously tested. That openness is not a weakness. It is a survival strategy. Perhaps the most important realization is this: quantum computers do not attack Bitcoin as an idea. They challenge certain mathematical tools Bitcoin currently uses. Tools can change, ideas endure. The belief that Bitcoin's fate hinges on a single cryptographic primitive misunderstands what Bitcoin actually is. It is a social system encoded in software, governed by incentives, consensus, and human coordination. Cryptography is its language, not its soul. When viewed this way, quantum computing stops looking like an executioner and starts looking like a stress test. It forces the system to confront uncomfortable questions early, while there is time to adapt. The danger, if there is one, does not come from quantum machines suddenly waking up and tearing Bitcoin apart. It comes from complacency, from assuming that because something has worked so far, it will work forever without evolution. Quantum computers are not gods. They are instruments, powerful, yes, revolutionary, potentially, but bound by physics, engineering, and time. And time, as we will see in the next part, is precisely what Bitcoin has on its side. One of the most persistent myths about Bitcoin is that it cannot change. The idea is comforting in a way. An unchanging system feels safe, predictable, immune to manipulation. But this belief, while emotionally appealing, misunderstands how Bitcoin actually survives. Bitcoin's strength has never come from being frozen in time. It comes from changing carefully, deliberately, and only when the cost of not changing becomes greater than the cost of adaptation. From the outside, Bitcoin looks rigid. Its monetary policy is fixed, its supply is capped, its issuance schedule is predictable down to the last decimal. These properties create trust in a world accustomed to inflation and uncertainty. But beneath that surface rigidity lies something far more flexible: the protocol itself, shaped by human coordination and economic incentives. Bitcoin has already changed many times, not recklessly, not overnight, but through slow consensus. Segregated witness altered how data is stored and validated. Taproot expanded privacy and scripting capabilities. Each change was controversial, debated, resisted, and eventually adopted because the network decided the trade-off was worth it. Bitcoin evolves not through authority, but through agreement. The quantum question fits naturally into this pattern. If cryptographic assumptions are threatened in the future, the response is not panic. The response is migration. Cryptography has always been a moving target. Algorithms rise, prove themselves, and eventually retire. The internet has gone through multiple generations of cryptographic standards without collapsing. Secure systems adapt because stagnation is the real vulnerability. What often goes unspoken is that Bitcoin has a unique advantage in this transition. Unlike closed systems, Bitcoin's entire security model is visible. Developers, researchers, and adversaries all examine the same code. Weaknesses are not hidden, they are anticipated. When post-quantum cryptographic schemes mature, Bitcoin can, in principle, integrate them through upgrades that preserve its core properties. Critics often imagine a dramatic moment where quantum computers suddenly appear, wallets are cracked, and chaos ensues. Reality does not work that way. Technological shifts announce themselves years in advance. Research papers appear. Benchmarks improve slowly. Institutions adapt long before crises occur. By the time a quantum threat becomes practical, the world will already be in transition. Another overlooked aspect is that Bitcoin does not exist alone in the cryptographic hierarchy. Banks, governments, military systems, and global communications all rely on similar or weaker assumptions. If quantum computers become capable of breaking Bitcoin signatures, they will also be capable of forging bank transactions, decrypting classified communications, and undermining national security. In such a world, Bitcoin would not be the first domino to fall. In fact, Bitcoin might be among the first systems to respond. Its decentralized nature allows experimentation at the edges. Developers can propose changes, users can test alternatives, miners can signal support, No central authority needs to approve the future. This is messy, slow, and inefficient by design, but it is resilient. There is also a deeper layer to the quantum discussion that rarely surfaces. Bitcoin's security does not rest solely on cryptography. It rests on economics. Even if an attack were theoretically possible, it would need to be economically rational. The cost of mounting a successful quantum attack would likely be astronomical, rivaling or exceeding the value it seeks to extract. Attackers do not operate in a vacuum. They operate under incentives. This economic dimension matters because Bitcoin was built to make attacks expensive and coordination costly. It is easier to participate honestly than to subvert the system. That principle does not vanish in a quantum future. If anything, it becomes more pronounced as technological complexity increases. There is also the question of who controls quantum computers. These machines, at least for the foreseeable future, will not sit on kitchen tables. They will belong to governments, research institutions, and corporations. Their use will be constrained by politics, regulation, and strategic considerations. The idea of anonymous attackers casually breaking Bitcoin with quantum laptops is not just unrealistic, it misunderstands how power actually manifests. Bitcoin's response to quantum computing is not denial, it is patience. The protocol does not rush to solve problems that are not yet real. Premature changes can introduce more risk than they eliminate. Bitcoin has learned, sometimes painfully, that caution is a feature, not a flaw. What emerges from this perspective is a quieter confidence. Bitcoin does not claim to be invincible. It does not promise eternal relevance. It offers something more grounded, a system willing to confront future challenges without surrendering its principles. Quantum computing, then, becomes part of Bitcoin's maturation process, a reminder that no system is final, and that resilience comes from adaptability guided by consensus, not fear-driven reaction. In the next and final part, we step back even further. Beyond algorithms and machines, beyond upgrades and attacks, we ask a more enduring question. What happens to Bitcoin as an idea in a world where even mathematics feels uncertain? When discussions about Bitcoin and quantum computers reach their deepest point, they often leave technology behind. Not because the technology no longer matters, but because something more fundamental begins to surface. If one day every cryptographic algorithm can be challenged, if every mathematical lock eventually meets a stronger key, then what exactly is Bitcoin protecting? At first, the question feels destabilizing. Bitcoin has always presented itself as precise, mechanical, and absolute. 21 million, immutable rules, verifiable truth. Yet beneath that precision lies a human intention that no machine can compute. Bitcoin was never just an engineering solution. It was a philosophical response to a world where trust had become abstract, centralized, and fragile. Quantum mechanics tells us that uncertainty is not a flaw in our measurements, but a feature of reality itself. Bitcoin, in its own way, responds to uncertainty by removing discretion. It replaces judgment with rules, promises with proof. The tension between these two ideas is not a conflict. It is a conversation about how humans organize meaning in an unpredictable universe. Even if quantum computing forces Bitcoin to evolve its cryptography, the essence remains unchanged. Bitcoin is not defined by elliptic curves or hash functions. Those are tools, chosen because they work today. Bitcoin is defined by voluntary consensus, by the refusal to grant any single entity the authority to rewrite the ledger of value. This is why predictions of Bitcoin's death often miss the point. Technologies die when their purpose disappears. Gold did not vanish when we learned nuclear physics. Writing did not end when we invented the printing press. They adapted because they served something deeper than their original form. Bitcoin serves the desire for economic agency. It gives individuals the ability to store and transfer value without asking permission, without trusting intermediaries whose incentives are opaque. That desire does not vanish when technology advances. If anything, it intensifies. In a future shaped by quantum computation, artificial intelligence, and systems too complex for any single human to fully understand, the need for transparent, rule-based coordination grows stronger. Bitcoin speaks to that need in a language that machines can verify and humans can agree upon. There is a quiet irony here. Quantum computing represents the cutting edge of centralized scientific effort, massive funding, specialized expertise, and controlled environments. Bitcoin represents the opposite impulse: decentralization, openness, and adversarial participation. They are not enemies. They are reflections of different approaches to power. If quantum computers reshape the technological landscape, Bitcoin will respond not by resisting change, but by reaffirming its core constraints. Scarcity will still matter. Consensus will still matter. The separation of money from discretionary control will still matter. These are social choices, not technical accidents. Perhaps the most important realization is this: Bitcoin does not need to be eternal to be meaningful. It needs to exist long enough to shift how humans think about money, trust, and authority. In that sense, its impact is already irreversible. Quantum computers may one day force Bitcoin to rewrite parts of its code. They may introduce new forms of cryptography that feel just as alien to us today as elliptic curves once did. But rewriting code is not the same as rewriting purpose. When future historians look back, they may not remember the specific algorithms Bitcoin used in its early years. They will remember that, for the first time, a global monetary system emerged that did not rely on violence, borders, or centralized decree. That achievement does not disappear because mathematics advances. In the end, the story of Bitcoin and quantum computing is not a story about destruction. It is a story about maturity, about a system confronting the limits of its assumptions and choosing evolution over fear. The future does not demand certainty. It demands adaptability, anchored in principle. Bitcoin, at its best, offers exactly that. And in a universe where even reality itself behaves probabilistically, perhaps the most radical idea is not perfect security, but shared agreement. That is something no machine, quantum or otherwise, can take away.